Okay. Hi guys, my name is Hannah Comiskey, and today I'm going to be speaking to you about estimating modern contraceptive use, moving from models to people. This is work that I've done with my supervisor, Dr. Niamh Cahill, and I'm part of the Department of Maths and Stats. So just a little background on my research. So where is this all coming from? Well, in 2012, at the London Summit of Family Planning, the FP, or Family Planning 2020 Global Initiative, was formed. And this had the idea of adding 120 million additional users of modern contraception from 69 of the world's poorest countries. And the aim of FP 2020 is to empower women by providing sexual and reproductive health services, information, and education. And by doing this, we're returning the right of choice to women, choosing whether, when, and how many children to have. So just some facts and figures about the impact of FP 2020. So in 2012, when it began, there were 260 million users of modern contraception in the participating countries. By July 2020, this had risen to 320 million, and that's an increase of 60 million women and girls around the world. So in that 8-year period and across the 69 countries, focus countries, the modern contraceptive prevalence rate, which is the proportion of women using modern contraception, rose from 31% to 34%. And this happened fastest in the Eastern and Southern Africa, where it actually raised 8%. So just even to measure the impact of this work in a year. So from July 2019 to July 2020, there were 121 million unintended pregnancies averted, 21 million unsafe abortions averted, and 125,000 maternal deaths averted. And this is all through the impact of supply of modern contraception to these women. And this is a huge initiative. So in 2019, there was $1.5 million US in funding supplied to this. So a lot of you might be thinking, okay, you're talking about FP 2020 and Hannah, it's now 2021. Where are you going with this? So we're now looking towards 2030. So this has been an 8-year arc of work, and it's been a huge kind of lots of people working together. So there's been governments, civil societies, multilateral organizations, donors, the private sector, and of course the research community. And this is we've all been working together to go towards this common goal of an additional 121 million users. So this has been extended to 2030 now in line with the UN Sustainable Development Goals, and we're going to strive towards the future that women and girls around the world deserve. So I'm just going to talk through some of the language that you might hear me use during this presentation. So I'm just going to introduce it very quickly first. So one of the first things I'm going to introduce is the Family Planning Estimation Model. So FP 2020, or FP 2030 now, as it's kind of called, uses a data-driven approach to monitor the progress of its goals. So it's really important that it's really in tune with its data and what's going on in all the countries. So the Family Planning Estimation Model creates these estimates of modern contraceptive prevalence. And it does this by using large-scale national surveys. And there's a few different types of surveys that it uses. It uses demographic health surveys, or DHS surveys, multiple indicator cluster surveys, and performance monitoring action surveys. Notably, DHS data is the gold standard of family planning data, and that's really important because it's got rigorous methodologies associated with its collection. It's very dependable. It's like the census of family planning data, so you can really depend on it and it's very accurate. However, because it's so rigorous and dependable, it's expensive to carry out. So if you think about this in context, we have 69 of the world's poorest countries. So you can imagine asking them to do these really expensive large-scale national surveys regularly it's just not an option. So as a result, this data is very sparse for these countries, but it is there. So alternatively, and this is something that my project is going to be looking at, is an alternative data source called service statistics. So service statistics are a grassroots data source, and they're collected as a byproduct of the family planning service delivery. So they're collected anyway, this is happening. And they're collected by technical officers on the ground in each country. So these are government employees that are collecting this data in every single country. So why aren't we using this all the time? If this is service statistics are so great, why aren't they all being used constantly? So some of the pros of service statistics are that, as I mentioned, they're available in every single country. They're cheap to collect because they're being collected anyway. They provide high geographic detail, so down to the micro level of like facilities, like where in the country, in the region, in like exactly where it came from. They're annually resolved, and this means they're available every single year, which is a really big thing. And as I mentioned, they're collected by local officers in each country. But they're not perfect. So service statistics are error prone, and this is mostly because they don't have the rigorous methodologies of the DHS. So they do tend to have issues with like human error and stuff. As a result, there does tend to be issues with variance and bias for the service statistics and the estimates that they produce. So Track 20, which is a group that are employed to monitor the progress of the FP 2020 Global Initiative. They hold workshops every year internationally for the technical or the local technical officers in each country. The officers bring their service statistic data, and as a group, they work through them to produce estimates of modern contraceptive use, or EMUs. Now, EMUs are a little different to modern contraceptive prevalence because they're biased versions of modern contraceptive prevalence. So they're related, but they're not the same. So how do you go from using service statistic data to creating an EMU, an estimate of modern use? And this is done through an Excel workbook. And the technical officers in each country will get this workbook and they'll use it to convert the service statistics into EMUs. And then that's used to inform each country's annual estimates of key family planning indicators. So the basic kind of idea behind the SS to EMU tool, which is what they call that Excel workbook, is that first of all, you start with your raw data, which is over here on the left of this arrow. So you start with your number of commodities to clients, facilities, family planning visits, family planning users, that kind of information. Then a number of adjustments and calculations occur within the Excel workbook. And these are applied to the data to turn them into EMUs. So some of the things that come out of this workbook is you can look at the estimated number of users, and this you can use this kind of information to flag outliers, inconsistencies in trends, and dramatic periods of growth or decline within a country. And then as well, of course, you get an EMU, which is the number of estimated modern contraceptive users over the total number of women in that country that could use modern contraception. So to kind of bring this back to what I'm doing then, so these are my research aims. So first of all, I'm looking at exploring the current steps that are taken to convert service statistics into biased estimates of modern contraceptive prevalence. I'm then going to look at developing a set of statistical modeling techniques to allow the propagation of uncertainty into these final estimates of modern contraceptive prevalence from service statistics. So at the moment, what happens is you get service statistics and you'll get an EMU, but there's nothing to say how confident are we in that estimate? Like, do we think it's really right, or is it, is there a really large kind of credible interval that goes along with that? So that's kind of what we're going to be looking at. In addition, we're going to create an R package that takes service statistic data and creates estimates of modern contraceptive use with uncertainty for any given country. And then in the long term, we're hoping to incorporate all of this into the existing family planning estimation tool. So it's all about making greater use of these service statistics because they are a really great resource. So I mentioned that there are a number of adjustments and calculations that occur to service statistics to make them estimates of modern use. And what we're looking at is where we can kind of incorporate uncertainty into these estimates. So things like when you're multiplying numbers together, like, well, those numbers, how confident are you in the numbers? And like, things that we're using, adjustments, how confident are we in these adjustments? So there's three main areas where we think we can really gain some uncertainty in the service statistic workflow. So the first is there's a public-private sector adjustment. And this basically, it adjusts the raw data to account for a potentially missing private sector supply. So what that means is when you have service statistic data, you might be given the service statistic data and told that this service statistic data only accounts for the public sector. And that's okay. And you're like, okay, but the public sector only accounts for maybe 70% of that particular contraceptive. So say it's like the pill. So then you know you only have 70% of all the pill commodity. So you have to scale things up. And that's what that adjustment is doing. So data may be upscaled to account for both sectors. And currently we're modeling that using Spline models, which I will talk to you about later. The next two, I'm not going to talk to you too much about today, but I'll just explain quickly where they are. So we have method continuation rates, and method continuation rates basically mean that if a person gets an IUD in year 0, or a group of people get an IUD in year 0, what proportion of that group move to year 1, keep the IUD in year 1, what proportion move to year 2, what proportion move to year 3, etc. So that's continuing to use the method over time. So that's what that is. Those are those rates. And we think that uncertainty can be kind of incorporated there. And then lastly, estimation of historical users. So this is how many users were already using modern contraception before we started to track with service statistics. So this is the number of users using a contraceptive method prior to the first year of data. And it uses both the continuation rates and adjusted commodities, but we won't need to worry about that today. So just to give you a look at the data set, so what am I working with? So I have 30 countries. Now I've just given you a subset of those countries on the right here. So what this graph is across the x-axis, or kind of going along the bottom, we have time, which is years. And then going up the top, which along the y-axis, we have the proportion of a particular contraceptive method that is coming from the public sector. Okay, we have a couple of different countries, and this data, I'm getting it from the DHS, which is the gold standard family planning data. And this will feed into that public-private sector adjustment factor step in the service statistics workflow. So you can see here, this illustrates my point very nicely that DHS data is not readily available for all countries, and it's definitely not available every single year. So you can see that some countries in the list have like a good bit of data, like Mali, but then there's some countries that only have one data point, and that's it. So Myanmar. And we're looking at 5 different types of contraceptive methods in this study. So how do you model that proportion coming from the public sector? Well, this slide, you might look at it and go, oh God, there's a lot of stuff going on here, but I'm going to break it down and I'm going to talk to you just about 2 models in particular today. But basically what we looked at when we were considering models was flexibility, was the first thing, and correlation. Okay, so the first thing I'm going to talk to you about is correlation. So when you're modeling data, the simplest model that you can fit is a straight line, right? It makes sense. If you have loads of data and you draw a straight line through it, that's a model. And that's what we did here up the very first model. So Y is the expected proportion of a contraceptive method in country C at time T supplied by the public sector. Okay, so that's that proportion. We have an intercept, which is alpha. And then we have a rate, which is theta, and just T for time. Okay, so if you think of the equation of a line, Y equals mx plus c, this is the same thing, right? It's just written a little bit differently. So what we're saying here is we're fitting a line, and we're interested in the rates we're interested in these slopes. So I'm going to talk to you about theta first, and I'll come back to alpha in a minute. So first of all, we're saying theta is, so for method M in country C, we're saying that theta comes from a normal distribution where that method is centered on some world slope for that particular method. Okay, so each method is independent and they're coming from some kind of normal distribution separately. Okay, so that's fine. But the next step is thinking about, well, what if instead of assuming all the methods are independent from one another? What if we said maybe they're not, right? And this is kind of intuitive, because if you think of a population, if there's a huge uptake in female sterilization, then you would think that the number or the proportion of people that are going to be using, say, the pill, that might go down, right? So you could think that there might be some kind of correlation structure that exists between these methods. And this is our next step. So the next model that we fit was saying, we're not worrying about flexibility right now, so we're just fitting the line. But this time, we're now saying that the slopes that are associated, where the rate of change that was associated within each of these methods, is they're correlated. And we create this correlation by using a multivariate normal distribution, where it's centered, all the methods are centered together on some world parameter, okay? And that's what's happening in this second model. Now, the second thing I said to you was flexibility, right? So you can imagine that straight lines aren't that flexible. They are straight lines, that's it, right? So if we wanted to gain some curvature within our model, we're now thinking about maybe incorporating splines. So for anyone who's not sure what a spline is a piecewise polynomial. So if you break up your x-axis into parts, and for each of those parts, you model a polynomial and you join them together. And there's maths going on under the hood here that will ensure that it is smooth. That's what we're using here. Okay, so a hierarchical penalized spline model. So that's number 3. So that's now where we're incorporating some more flexibility into our model. And we're saying here that the coefficients of each polynomial, okay, so beta, m, c, k, we're saying that, and what this is the penalized part of it, we're saying that the difference between one set of coefficients and the previous coefficients, we expect that to be 0, okay? So we don't want huge jumps between each of our polynomials. So we're penalizing it there to say that we really want these coefficients to be similar to each other, moving from one part of the x-axis to the next. Okay, and this is where we get a little bit more flexibility in. So now we have flexibility, but let's bring back in our correlation. So instead of saying now that all of the methods are independent again, we're going to say, okay, let's bring in the correlation with the flexibility, and we get to our last model. This last model says that the coefficients of our splines are related to one another, and that we expect it to come from a multivariate normal distribution. And so we're sharing information across the methods here. So today I'm going to talk to you about the simplest model and kind of the most complicated model. So we're going to talk about the hierarchical linear one and the hierarchical penalized spline with correlated method coefficients. So the first model and the fourth one. So just before I jump off into how they perform, I just want to speak to you guys about what I said about the intercept. So I said that in every single one of these models, we have the word hierarchical. And for people who aren't sure what hierarchical means, I'm just going to explain it very quickly here. So in my data, I have data along the bottom here, and you can see that in the diagram below. So I have data points, and each of these data points is like a proportion in a country for a method at time, right? So hierarchy, basically what we want in Bayesian statistics is that we want to be able to group our data and then group it again, so that by grouping, we're sharing information and we're gaining more understanding about the particulars of the data points. Okay, so if you think about it, we'll start on the data level and we just have unique data points, but we can group these data points into countries. Okay, and when we group these into countries, then what we're doing is we're sharing information across data points, but within countries. Okay, and then we can group the countries. Now we can group them into regions and continents, but we found that even if you add that extra complexity, not a whole lot is gained in this particular instance. So we went straight from going, okay, grouping them into countries, and now we're just going to group them into worlds. And this feeds back. So if you think about it, we now have a world parameter, which each of the countries can feed off of, which makes sense. And then all of the data points can feed off a particular country. So now we're sharing information and gaining better understanding of our data through this grouping hierarchical structure. And that's what's going on here for our intercepts. So if we compare the output of our spline models with our simple linear regression. So what I have here is for 7 countries here, I have observed data, which is our blue. So this is like the actual data that I put in. Then we have in green, we have the linear model, and the line going in the center, that kind of dark green line, that is the estimates for every year according to the linear model. And then the dotted lines along the outside, that is the 95%, that's the boundary of the 95% credible interval. And similarly, we have our multivariate normal p-spline, which is in purple. Okay, so you can see here that, I think the first thing to note actually is that neither of them do particularly terribly. Like they actually do quite a good job, even the simple linear model. But you can really see that the p-spline model really does fit the data better, and it is capturing that curvature and it's smoother through the data. So in particular in the Philippines, you can see here that the linear model is losing a lot of that curvature by just going straight down, whereas the p-spline model is capturing that really nicely. Some of you might notice that there are 2 shaped dots on this diagram. So there's circles and then there's triangles. The circles are what we call training data. So that's what I gave my model to kind of train and create like the model basically with. And then the triangles are test data. So it's data that I didn't show my model. And I just wanted to see how well my model estimates that. So are the model estimates lining up with the test data? You can see that it does well. There's some points that the model, the multivariate normal model, does capture better than the p-spline or the linear model. And this is for oral contraceptive pills. So then comparing models. So the model that I want you to look at, first of all, is the linear model, and that's the top one. So the linear model performed relatively well. It got 78% of the test data points within that credible interval. So it predicted, I think the test data lies between here and here, and 78.1% of the time it was right. The average error size, so how much each estimate was wrong by in the linear model, was 0.29 or 129. Now the p-spline, multivariate p-spline model is the 4th line on this table. And you can see here that it actually does a good bit better with the test data. So in this instance, it captured 88.6% of the data points, the test data points within that 95% credible interval. But the root mean square error was a little bit larger, but not hugely larger. So it's okay. Some more graphs that I want to show you. So on the left, this is comparing the root mean squared error, or the average error size, for a couple of different models that we fit. I have highlighted the normal p-spline model with the little orange arrow, and the simple independent linear rates model with the blue arrow. And along the bottom is the size of the root mean squared error, and obviously going up the top is the name of the models. So you can see that the simple independent rates linear model was the smallest. It did produce the smallest root mean squared error, but as you can see, they're actually all very close. So even though it's the smallest, it's not the smallest by a lot. And then on the right here, what I'm looking at is I'm comparing the size of the credible intervals. So if the credible interval is huge, then that's not so good, right? So we don't want absolutely massive credible intervals. We want them to be relatively small. So you can see, obviously, the simple independent linear rates is the smallest. And this is because it's a linear model. So that's not hugely surprising. But the normal p-spline one, it's not. And that, again, is in the orange arrow just there to highlight that to you that I've highlighted them. it's not making massive credible intervals in comparison to the other models. So we're happy enough that it's not just producing these huge credible intervals and just collecting all the data by proxy. It's kind of in keeping with all the other models. So you can see that along the x-axis here, we have the range or the size of the credible interval. So obviously, if the credible interval was size 1, it would just cover the whole graph. So we don't want that. So you can see that it's okay. It's at around, what, like 37%. Okay, so zooming in then on the performance of this hierarchical penalized spline model. I've just picked 2 countries. I have Ghana here on the left and Benin on the right. I just picked them randomly. There's no point. There's no rhyme or reason behind this. So along the x-axis, again, I have time, and going up the y-axis, I have the proportion of a particular method coming from the public sector. The colored dots are the data, and the black line is the estimate, with the gray being the credible interval. So if I bring your attention over to Ghana, we can see here that it's actually doing a pretty good job. It's capturing the shape of the data nicely. It's not overfitting it. It's doing nicely. The credible intervals aren't massive. And you can see then in Benin, which is on the right here, that Benin only has 1 data point for female sterilization. And this is really important because you can see that when there's in the absence of data, the credible intervals do get larger. So when the model is informed, the credible intervals get smaller. You can see again that it does a nice job. It's capturing the shape of this data nicely. So the hierarchical penalized spline model with the correlated methods, so we're sharing information across methods, it really does work nicely for this data. So my other work then, so I've been kind of doing 2 things since September. The other work that I've been doing is taking this Excel workbook that I talked to you about earlier and turning it into an R package. So on this slide, I have just a screenshot of what the Excel workbook looks like. You can see that there's a bunch of tabs going along the bottom. There's actually way more tabs. It didn't capture it all. But yeah, so the basic idea is that I wanted to take that Excel workbook and now change it into an R package so that data scientists and people like myself don't have to use Excel. So the aim of the package is to complement the Excel and the methodologies that are used in it, and also incorporate some of the new methodologies that we've been working on ourselves. And my GitHub is there for anyone who is interested. So there are a few little process differences because obviously we're moving from Excel to R, so there does going to have to be some process differences. So originally in the Excel workbook, the users moved through the workbook, filling in the data and reviewing the results in each tab. Then they see the data move from start to finish, and at each step they start to finish through each step to produce an EMU. They have all the tables and graphs within that one Excel workbook, and they can go between them very easily and quickly. And the Excel workbook has a lot of tabs, but it also has a lot of repetition. So for the 4 types of service statistic data, there's 4 repeats of the same tabs. Now, in comparison, the SS to EMU package, which is the one that I've been working on, what the user does is they fill in 5 template Excel files before use. So this is just giving the package some basic information about the country, what sectors you have reporting. So that's for that public-private sector that I was talking about. Some information, some quantities on like what kind of contraceptives and the quantities that are associated with those, that kind of information. Then what the user is required to do is provide 3 functional arguments. So they need to say whether or not they want to include condoms from their final estimate. Condoms are very tricky to model, and a lot of the time they're left out because they're very hard to monitor. So someone could take like a bunch of them, but they mightn't use them. So it's very hard to know. Whereas say with like a pill, you take that every single day, you come back, you get your repeat prescription. They're a lot easier to monitor. So you have to decide whether you want to include or exclude condoms from your final estimates. Then also you can view a particular year of service statistic data in greater detail. So you have to give the name of the year that you'd like to view in greater detail. And then also you can view a particular method in greater detail. So if say you decide, oh, I want to look at the pill in detail, you just give the name of the pill. So those are the three arguments to functions that you just need to it depends on the user. Everything else is fixed. So then the user runs 15 functions, just press click and go. And this will create estimates of modern use, which are exported to a CSV file within the data folder. And of course, the user can review individual tables and graphs at the main steps. So there are some calculation differences, mostly because that we've been incorporating our modeling into it. So currently within the Excel workbook, the missing private sector adjustment is calculated from the last DHS figure. So this is an issue because if the last DHS figure was in 2004, then that's the number that you're going to be using, even though it's 2021. So you can see where this is becoming an issue, and this is what we're kind of working on at the moment. And then that DHS figure is the same for every single year of service statistic data that you have. So 2016, 2017, all the way up to 2021, that'll all use the 2004 figure. Whereas in the package, because we've been modeling the private sector or the proportion coming from the public sector using those P-splines, we now have annually resolved estimates or estimates for every year. This means that we can create a unique adjustment factor for every year of data that we have, and then each year gets its own adjustment or own proportion. So what are the next steps for the package and for things that I'm doing? So I hope to include uncertainty bounds for the private sector adjustment. So and then model the areas of uncertainty that I talked about before with uncertainty bounds. So getting those credible intervals for all of the estimates and numbers that we're using. Then using those estimates with uncertainty, we can quantify the overall uncertainty for the EMUs, which is what we're looking to do. So we want to gather some credible intervals for those EMU estimates. And then lastly, at the moment, the SST EMU package has a bit of a black box feel because you open it, you run your functions, and they just kind of go. But what we're hoping to do is create a shiny app that will emulate the look of the Excel so that when it comes to people using it, that they'll be more used to using it, and it's something that they're kind of used to looking at, right? So to conclude, the Family Planning 2030 initiative requires ongoing family planning performance data. And this is really hammered home in the 2030 focus statement, where it says that to expand this work, they want to ensure that the data is timely, key gaps in the data are filled, and a greater capacity for data use is built at a country level. So this really is the time for service statistics to be really utilized and come into their own. So it's really important to exploit the resources that we have at our disposal when monitoring these family planning indicators. And making better use of the service statistics is a vital piece of that puzzle when modelling annually resolved estimates of modern contraceptive prevalence. So accounting for those uncertainty within the service statistics will actually improve their usability and value within the family planning estimation model, which is really important. So, and I think the overall thing to remember here is that we're actually working, like, you can get very caught up in the numbers, but ultimately what we're really working towards is a future where women and girls everywhere have the freedom and ability to lead healthy lives, making their own informed decisions about contraceptive and whether or not to have children, and that they can then go on to participate as equals in society and development. So that is the ultimate 2030 vision. Thank you.
Thanks so much, Hannah. That was fascinating. It's very detailed there. Just to let everybody know that you're welcome to put questions for Hannah in the chat area, or if you want to unmute yourself and ask instead, that's also fine. So please feel free to do that. There's quite a lot there covered in relatively short time, so I'm sure everybody has a chance to think about that.
Yeah, digest.
People are with a question. You know the way you were comparing the models using something called leave one out?
Yeah.
Does that work by leaving out a single data point and seeing how well it predicts?
Exactly, that's exactly what it is. So if I just bring you back to this this particular graph, So what we've got here in blue is we've got circles, which are the data that I've trained my model on. And then the triangle, the blue triangle, is the point that I've left out. And I wanted to see how well does each model predict that point. So how close can it get to that point? And you can see that the Spline model, which is the kind of dark purple line, actually does a pretty good job at doing it. And that's what we're looking at when we look at these validation results. That's what that means. What proportion of those triangles can the models correctly kind of estimate?
Cool.
Cool. Great question.
Any idea why the leave one out thing will be better, but the mean square will be worse? Or is it overfitting or something? Or?
Yeah, see, it's hard to know because there's some, like, you can't see it here, but there are other countries where they're actually make huge jumps. And I think that's where it's going from, because the Spline model will go with the data that it has. And then in the absence of data, it goes straight across. So those huge jumps get kind of left behind a little bit. So we're going to be, that's actually kind of something that we're looking at now, is like kind of how can we improve that kind of very unusual behavior around those big jumps.
Cool.
Great.
Thank you.
Thanks.
Hey, Hannah.
Hey.
Thanks for a really good talk. I was wondering, with regards to your covariance structure in your multivariate normal distribution, how did you estimate your correlations, or did you give a prior for them, or?
Yeah, no, that's a great question. So what we did is we actually looked at doing it both ways. So we looked at putting a prior on the correlation structure and estimating it. And it turned out that there actually isn't really enough data to put a prior on it. So the model wasn't learning a lot from the prior. So we actually just used fixed estimates. So we estimated the correlation and then left it as a fixed estimate rather than just using a prior, because the model was kind of getting a little bit lost.
Okay, cool. Thank you.
Thank you.
Can I ask a question, please?
Yeah.
Hi, Hannah.
Hello.
It's Ed, if you can't see me.
I know, I can see me.
I really like the Spline model. It's brilliant. There was just two things I wanted to ask about it. When you showed the graphs comparing the two models, that was for a single type of contraceptive, right? The proportion for
Here, this one?
Yes.
Yes, so
Was
this
that,
is for oral contraceptive pills.
Yeah. So my question was, did you estimate the proportion of each type of contraceptive separately, or did you fit a single model for all different types of
because that's a great question. So because of the multivariate normal, all the contraceptives go in together. So it's the one model that comes in.
Yeah, exactly. Yeah.
And I just split the estimates and came out and took out the pill and basically plotted that. So that's why they're not there. But I do have the estimates for the other ones. So if you're actually interested, I can give you a look at them.
Yeah. That's great.
Hannah, I just see a message or a question coming in there from Peter Delaney. He's just wondering, what does public and private sector mean?
Oh yeah, so public sector and private sector is referring to basically the source of the contraceptives. So public health would be like your public hospitals. That's the public sector, or your GP. And then your private sector is like your private hospitals and like private pharmacies and people who are buying it themselves rather than being supplied by the government. Is that okay? That's a great question,
so. Yeah,
actually.
That's perfect, Hannah. Thanks.
Brilliant, thanks.
Yeah.
I should have clarified that.
Be any other questions for Hannah? Either in chat, or feel free to unmute if you want to ask as well. Just while you're thinking there, this talk obviously is being recorded, so we'll be able to share a recording of the talk too. So, and I'm sure Hannah will welcome questions after the fact as well too.
Oh yeah, absolutely. If anyone has any questions or ideas or comments or anything, I'd love to hear them. It would be great to get chatting to people about it.
I think also it's going to be available on YouTube.
Perfect.
So.
Okay, if there's no further questions for Hannah, do you want to wrap up there, Hannah?
Yeah, perfect. So I'd just like to thank everyone for coming along, and thanks to the Maynooth Library for having me, and thanks to my supervisor, Niamh Cal, and the FP 2020 team for allowing me to do this. Great. Thank you very much, guys.
And thanks very much to yourself, Hannah. We really appreciate you taking the time to speak to us about your work today. It was really great to hear it. So thank you very much indeed.
Thank you very much.
Thanks so much.